Welcome to your personalized deep dive into the world of PostgreSQL replication. Looks like you've given us a ton to work with.
Yeah.
Everything from the basics to some really powerful tools like Slony and pgpool.
Yeah.
You're clearly aiming for a setup that keeps your data safe, even if things go wrong. And of course, speed is always a factor.
It's fascinating how PostgreSQL offers so many ways to approach this, from simple backups to those complex multi-master setups. Each has its own pros and cons, so understanding your specific needs is really the first step. If you're dealing with huge amounts of data, for example, the time it takes to create a base backup becomes a major consideration.
Absolutely. Nobody wants to be twiddling their thumbs for hours waiting for things to sync up. One of the first things that caught my eye in your research was the CAP theorem. I have to admit, it sounded a bit intimidating at first, but it actually highlights a pretty fundamental truth about systems like the ones you're building.
The CAP theorem essentially tells us that in any distributed system, we can only guarantee two out of three things: consistency, availability, and partition tolerance.
So, consistency means everyone sees the same data at the same time. Availability means the system's always up and running. And partition tolerance means it can keep working even if part of the network goes down. That's a tough choice. How do you even begin to decide which two to prioritize?
You have to consider the specific needs of your application. For example, if you're running a bank, you absolutely need to ensure that every transaction is accurately reflected across all systems. You can't have someone withdrawing money from an ATM if the system can't guarantee their account balance is correct. In this case, you might be willing to sacrifice a bit of availability in the event of a network issue to ensure that consistency.
That makes a lot of sense. You also included some information about the limitations of the speed of light and how that affects data transfer. I never thought about physics playing a role in something as abstract as data.
It's a really important concept, especially as systems become more geographically distributed. Even though we think of data moving at the speed of light, it still takes time for information to travel between servers located across the globe. That delay, which we call latency, can have a huge impact on your replication strategy.
So you're saying that even if I have the fastest network in the world, there's always going to be some lag because of the physical distance between servers.
Exactly, and that lag becomes more pronounced the farther apart your servers are. It's a fundamental constraint that forces you to make careful choices. Do you need absolute up to the millisecond consistency? Or can you tolerate a small window of potential data loss in exchange for faster performance?
It sounds like choosing the right replication method is a key part of balancing these trade-offs. I noticed that your research mentions several different types of replication offered by PostgreSQL.
Yes. PostgreSQL offers a variety of techniques, each with its strengths and weaknesses. Let's start with the two main categories: asynchronous and synchronous replication.
What's the difference between these two approaches?
Asynchronous replication is like sending a regular letter. It's quick and efficient, but there's a small chance the letter might get lost in the mail. With synchronous replication, you're opting for something closer to a courier service. You're guaranteed that the letter will arrive, but it will take a bit longer and cost more.
So asynchronous replication is faster, but has a small chance of data loss, while synchronous is slower, but guarantees that no data is lost. How do I know which one is right for my situation?
It all depends on your tolerance for risk and the specific requirements of your application. If you're handling financial transactions, you absolutely cannot afford to lose any data. So synchronous replication is the way to go, even if it means a slight performance hit. On the other hand, if you're replicating something like log files, where occasional data loss wouldn't be a major issue, asynchronous replication would likely be a better fit. You get the speed and efficiency without taking on unnecessary risk.
That makes sense. It's all about choosing the right tool for the job. Is there anything else I should consider when choosing a replication method?
PostgreSQL also offers different methods of replication: physical and logical.
What are the key differences between physical and logical replication?
Think of physical replication as creating a photocopy of a document. You get an exact duplicate. Logical replication is more like summarizing the key points of a document. You're replicating the meaning, not the exact structure.
So physical is for when you need a perfect, identical copy, and logical is more flexible. When would I use each method?
Physical replication is great for disaster recovery situations, where you need to create an exact duplicate of your database at a different location. Logical replication offers more adaptability because it replicates changes at the SQL level. You can even use it to replicate between different versions of PostgreSQL, or even to other types of database systems.
It sounds like PostgreSQL offers a lot of flexibility when it comes to replication. We've talked about asynchronous versus synchronous and physical versus logical. Are there other factors I should be aware of?
Absolutely. You also mentioned sharding in your research, which is a technique for distributing data across multiple servers to improve performance.
Yes. I'm interested in learning more about sharding. It seems like a powerful technique for handling large data sets and high-volume traffic.
Imagine you have a massive table with millions of rows. Trying to query that on a single server can be incredibly slow. Sharding allows you to break that table into smaller chunks and distribute them across multiple servers. Think of it as a divide and conquer strategy for data management.
So, instead of one server trying to handle everything, you have a team of servers working together. That sounds much more efficient. But are there any downsides to sharding?
Sharding does come with its own set of challenges. For example, one of your sources highlighted the problem of querying different fields. If you divide your data based on user ID, for instance, then trying to query by username can become a nightmare.
That makes sense. If the data is spread out across multiple servers, it could take a long time to find what you're looking for.
Exactly. And this is where things can get a bit tricky. One way to address this issue is to maintain full replicas of small, frequently used tables. This might seem counterintuitive, but it's often more efficient than trying to query multiple shards for a small piece of information.
So, in some cases, it's better to have some duplication to avoid complex queries across multiple servers. What are some other considerations when it comes to sharding?
Another important factor is how you distribute the data across the servers. A technique called hashing is often used to ensure a more even spread of data. Instead of dividing data alphabetically, which can lead to imbalances, hashing assigns each piece of data to a server based on a unique pair generated by a mathematical function.
Hashing sounds like a more efficient and balanced way to distribute data. It seems like there's a lot to think about when it comes to sharding.
Sharding is a powerful technique, but it's not a magic bullet. You have to carefully consider your data model, query patterns, and performance requirements to determine if sharding is the right approach for your needs.
I'm starting to see that there are many factors to consider when designing a PostgreSQL replication strategy. Are there any tools that can help manage the complexity of replication, especially when it comes to techniques like sharding?
You're right. Managing replication can be challenging, fortunately. PostgreSQL has a rich ecosystem of tools that can help simplify and optimize the process. In your research, you mentioned several of these tools, like pgpool and Slony. Let's take a closer look at those, and some others that might be helpful for your situation.
Okay, let's dive into the world of PostgreSQL replication tools. What can you tell me about pgpool?
pgpool is a powerful tool that can handle load balancing and connection pooling for PostgreSQL. It acts as a middleman between your application and your database servers, distributing queries and connections to ensure that no single server gets overwhelmed.
So, pgpool helps improve performance and prevents bottlenecks by distributing the workload across multiple servers. What about Slony? I understand that it's a tool for logical replication.
Slony is a robust and flexible tool that allows you to replicate data at the logical level, meaning it replicates changes based on SQL statements rather than physical data files. This makes it a good option for replicating data between different versions of PostgreSQL or even to other database systems.
It sounds like Slony is a good choice for situations where you need more flexibility and control over what data gets replicated. Are there any other tools I should be aware of?
Absolutely. Another tool worth exploring is PostgreSQL. It's a distributed version of PostgreSQL that's specifically designed for horizontal partitioning and query distribution.
So, PostgreSQL is like a sharding expert, built to handle the complexities of dividing data across multiple servers and managing queries that span those servers.
You could say that. It provides a consistent view of the data, even though it's physically spread out across multiple servers. Another tool that you might find useful is PL-Proxy.
What's PL-Proxy do?
PL-Proxy acts as a middleman between your application and your database shards. It helps route queries to the appropriate servers, making it easier to manage the complexity of sharding. You can think of it as a sharding manager, taking care of the low-level details so you can focus on your application.
These tools are starting to sound like a must-have for managing complex replication setups. Are there any other tools that stand out?
One more that you might find interesting, especially for geographically distributed systems, is BDR, which stands for bidirectional replication. It allows you to set up multi-master replication.
Multi-master replication, that sounds powerful, but also potentially complicated.
It is a powerful feature, but it's important to be aware of the potential for conflicts. When you have multiple servers acting as both masters and slaves, we'll dive deeper into conflict resolution later in our deep dive. And finally, there's walbouncer.
What does walbouncer bring to the table?
Walbouncer is a specialized tool that allows for selective replication. It acts as a filter, allowing you to choose which parts of the database to replicate to a particular server.
So,
Ooh.
it's like choosing which chapters of a book to copy. Instead of having to copy the entire thing, that can be really useful for geographically distributed systems, where you might not need all the data in every location.
Exactly. And that brings us to the end of our initial exploration of PostgreSQL replication tools. As you can see, there's a wide range of options available, each with its own strengths and weaknesses. The key is to choose the right tools for your specific needs.
This has been a great overview. We've covered so much ground already,
Okay.
from understanding the fundamentals of replication to exploring some of the tools available. It's clear that PostgreSQL offers a lot of flexibility when it comes to designing a replication strategy.
It's been a pleasure sharing this knowledge with you. Now that we have a solid foundation, let's dive deeper into some of the key aspects of replication, starting with conflict resolution in multi-master setups.
Sounds good. I'm eager to learn more about how to manage the complexities of multi-master replication. Let's do it.
Okay. Okay, so we've talked about multi-master replication and hinted at the potential for conflicts. Can you elaborate on what those conflicts look like and how they're handled in PostgreSQL?
Sure.
Let's use a simplified example. To illustrate how conflicts can arise in a multi-master setup, specifically with BDR, which you mentioned earlier, imagine we have a table called counter with just one column called id. It starts with the value 1, and we have 3 servers all replicating with each other using BDR.
Okay, so each server has its own copy of this counter table, and they're all supposed to stay in sync.
Now imagine each server runs a script. That increments that id value 10,000 times. Ideally, you'd expect the final value in the counter table to be 30,001, 10,000 from each server plus the initial 1. But because BDR is asynchronous, meaning changes aren't replicated instantaneously, conflicts are likely to occur.
I see where this is going. If one server increments the counter to, say, 5, and another server increments it to 6 at roughly the same time, based on its own copy of the data, they're going to end up with different values.
Exactly. This is where BDR's conflict resolution mechanisms come into play. BDR keeps track of all these changes and detects conflicts when they occur. Then, it uses predefined rules to decide how to resolve those conflicts.
What kind of rules are we talking about here? How does BDR decide which change wins?
One of the most interesting, and perhaps unexpected, ways BDR can resolve a conflict is by simply skipping one of the changes. This might seem counterintuitive, like you're losing data, but it's a crucial mechanism for maintaining data consistency.
I'm a little confused. How can skipping a change be a good thing? Wouldn't that lead to inaccurate data?
Think back to our counter example. If every single change was applied, even when conflicts occur, you'd end up with a final value much higher than 30,001. The counter would be wildly inaccurate.
Right, because each server is blindly incrementing the counter based on its own potentially outdated information. So skipping a change can actually help prevent those wildly inaccurate results.
Exactly. By strategically skipping certain changes, BDR ensures that the final value is at least within the realm of possibility. It might not be the exact value you'd expect if every change was applied sequentially, but it prevents the counter from spiraling out of control.
That makes sense. It's like choosing the lesser of two evils, a slightly off value versus a completely nonsensical one. But how does BDR decide which changes to skip? It seems like that could be a pretty important decision.
You're right, it's a critical part of the process. BDR can use several different strategies, but a common approach is to prioritize changes based on timestamps. The change that happened first, according to the timestamp, is more likely to be applied.
So it's kind of a first-come, first-served approach to conflict resolution.
You could think of it that way, but it's important to remember that even with this timestamp-based approach, there's always a chance of data loss. If 2 changes happen very close in time, BDR might skip a change that was actually valid.
That's a bit unnerving. Is there any way to guarantee that no data is lost in a multi-master setup?
Unfortunately, in a truly distributed, asynchronous system like BDR, there's no foolproof way to guarantee 0 data loss. There will always be some level of risk, especially when multiple servers are independently making changes.
So it's a trade-off. You gain the flexibility and scalability of a multi-master setup, but you have to accept the possibility of occasional data loss due to conflicts.
Precisely. That's why it's crucial to understand how BDR works and carefully design your applications and data model to minimize the likelihood of conflicts.
It sounds like the best way to deal with conflicts is to avoid them altogether if possible. What are some strategies for minimizing conflicts in a BDR environment?
One effective strategy is to partition your data in a way. That reduces the chances of concurrent changes to the same data. For example, if you're working with user data, you could shard the data based on user ID. This ensures that changes to different users are handled on different servers, reducing the chances of conflicts.
Ah, so it goes back to that sharding concept we discussed earlier. By spreading the data out across multiple servers, you reduce the likelihood of two servers trying to modify the same piece of data at the same time.
You got it. Another strategy is to use application-level logic to handle potential conflicts. For example, you could implement a technique called optimistic locking, where your application checks for changes to a record before attempting to update it. If it detects a conflict, your application can handle it gracefully, perhaps by prompting the user to review the changes, or by merging the conflicting updates.
It seems like a combination of database-level techniques like sharding and application-level logic can go a long way in creating a more robust system that's less prone to conflicts.
Exactly. It's all about taking a holistic approach, thinking about both the database design and the application logic to minimize the chances of conflicts arising in the first place.
Okay, so we've covered conflict resolution and strategies for conflict prevention. What about monitoring? How do I make sure my BDR setup is healthy and running smoothly?
Monitoring is absolutely essential for any replication setup, especially multi-master configurations. You need to keep a close eye on things like replication lag, conflict occurrences, and the overall health of your servers.
What tools or techniques can I use to monitor a BDR setup effectively?
BDR provides some built-in tools and metrics that can give you valuable insights. For example, you can monitor the replication lag, which tells you how far behind the slaves are compared to the master. BDR provides a system view called bdr.bdr nodes that shows you the current replication status of each node in your cluster.
So I see at a glance, if any of my servers are falling behind, what should I do if I notice a significant lag?
It depends on the specific situation. A small amount of lag is usually normal, especially in a busy system. But if you see the lag consistently growing, it could indicate a problem, like network issues, or a server struggling to keep up with the workload. You'll need to investigate the root cause and take appropriate action, which might involve addressing network bottlenecks, upgrading hardware, or optimizing your database configuration.
Monitoring lag sounds important. What other metrics should I be paying attention to?
Another crucial aspect to monitor is conflicts. Even though BDR handles conflicts automatically, it's important to understand how often conflicts occur and how they're being resolved. BDR logs conflict information to a table called bdr.bdr conflict history, which you can query to see the number of conflicts, how they were resolved, and what data was affected.
So I can actually see the history of conflicts and how BDR handled them, even if it resolved them silently in the background. What can I learn from this conflict history?
The conflict history can be invaluable for understanding how your system behaves under load and identifying potential issues with your data model or application logic. For example, if you notice a particular type of conflict happening frequently, it might indicate a flaw in your application design or a need to adjust your sharding strategy.
It sounds like the conflict history can provide really valuable insights. For fine-tuning my replication setup, is there anything else I should be monitoring?
It's also crucial to monitor the overall health of your servers, checking things like CPU usage, memory usage, and disk space. If any of your servers are experiencing performance issues, it can impact the replication process and the overall stability of your system.
Right. It's not just about the database itself, it's about the entire infrastructure that supports the replication process.
Absolutely, it's all connected. And one final thought on monitoring. Don't rely solely on automated tools. It's essential to have human eyes on the data, looking for patterns and anomalies that might not be obvious to a machine.
So it's a combination of automated monitoring and human intuition, working together to keep the replication system running smoothly. It sounds like a lot to keep track of.
It can be challenging, but effective monitoring is essential for ensuring the reliability and integrity of your replicated data. Now that we've discussed conflict resolution and monitoring in detail, let's shift our focus to another critical aspect of PostgreSQL replication: backups.
Backups. I thought that with all this sophisticated replication in place, backups might be a thing of the past, but I have a feeling that's not the case.
You're right, backups are still absolutely crucial, even in a replicated environment. They provide an essential layer of protection against data loss, especially in those catastrophic scenarios that replication alone can't handle.
Okay, so backups are like the ultimate safety net,
Yeah.
just in case everything else fails. What are my options for backing up PostgreSQL data?
PostgreSQL offers several approaches to backups, each with its own trade-offs. One common approach is to use the built-in tool called PG-based backup. It creates a consistent snapshot of your database, even while it's running.
So I don't have to shut down the database to take a backup. That's convenient.
Exactly. PG-based backup works by copying the database's data files and the transaction log, ensuring that you capture all the information needed to restore the database to a consistent state.
So PG-based backup is a good option for creating full backups. Are there other approaches I should know about?
Another option is to use file system level backups, using tools like rsync, or even simply copying the files. This approach can be simpler to implement, but you need to be careful to ensure the backup is consistent.
What do you mean by ensuring the backup is consistent?
When you're dealing with a live database, changes are happening constantly. If you simply copy the data files while the database is running, you might end up with a backup that reflects only part of those changes, leading to data corruption. Or an incomplete backup, you need to make sure you capture a complete and consistent snapshot of the data.
I see, that makes sense. So what's the best way to ensure consistency with file system level backups?
There are a few techniques you can use. One approach is to briefly pause the database activity, take the backup, and then resume activity. Another option is to use a technique called snapshotting, which allows you to create a consistent view of the data at a specific point in time without having to stop the database.
Those sound like effective ways to ensure consistent backups. Are there any other essential considerations when it comes to backups?
One final and crucial point to remember is the importance of offsite backups.
Why are offsite backups so important? Isn't a backup in a different location enough?
Imagine a scenario where a fire or natural disaster destroys your primary data center. If your backups are also stored in that same location, you've lost everything. Offsite backups provide redundancy and ensure that you can recover your data, even in a worst-case scenario.
That's a good point. It's like having a spare key hidden somewhere safe,
Yeah.
just in case you lose the original.
A perfect analogy. And with cloud storage becoming increasingly affordable and accessible, offsite backups have never been easier to implement. You can use cloud services to store your backups in a secure, geographically diverse location, adding an extra layer of protection for your valuable data.
Okay, so we've covered a lot of ground. From understanding conflict resolution and monitoring to the importance of backups, it's clear that ensuring data integrity and availability in a replicated environment requires a multifaceted approach. What's next on our journey into the world of PostgreSQL replication?
We've talked about replication as a way to keep data safe and synchronized. But what if we take a step back and think about replication in a broader context? What if we leverage replication not just as a safety net, but as a fundamental building block for achieving high availability?
High availability, that's a term I hear a lot, but I'm not entirely sure I understand what it means in the context of PostgreSQL replication.
High availability means designing your system in a way that minimizes downtime and ensures that your applications remain accessible, even in the event of hardware failures, software crashes, or network outages. Replication plays a crucial role in achieving high availability because it allows you to have redundant copies of your data, ready to take over if the primary server becomes unavailable.
So high availability is all about ensuring that your PostgreSQL database is always up and running, regardless of what challenges might arise.
Exactly. And one of your sources highlighted Linux HA, a powerful framework for achieving high availability in a Linux environment.
I've heard of Linux HA, but I don't know much about it. How does it work with PostgreSQL?
Linux HA, which stands for High Availability, is a collection of software components and tools that work together to monitor and manage various resources in a Linux cluster. It can manage things like network interfaces, file systems, and applications, including PostgreSQL.
So Linux HA can act as an overseer, making sure that all the pieces of my infrastructure are working together to keep my PostgreSQL database available.
Precisely. In the context of PostgreSQL, Linux HA can be used to set up a highly available PostgreSQL cluster. It can monitor the health of your PostgreSQL servers, detect failures, and automatically switch over to a standby server if the primary server goes down.
That sounds pretty sophisticated. Can you walk me through how this failover process actually works?
Imagine you have two PostgreSQL servers set up in a Linux HA cluster. One server is the primary server, actively handling database operations, while the other server is a standby server, passively replicating data from the primary server. Linux HA constantly monitors both servers, checking their health and responsiveness.
So if the primary server crashes, Linux HA will automatically detect the failure and promote the standby server to take over.
Exactly. Linux HA will promote the standby server to become the new primary server, making it available for applications to connect to. This process, known as failover, typically happens automatically and within a short time frame, minimizing the impact of the failure on your applications.
That's impressive. It sounds like Linux HA can be a powerful tool for ensuring high availability for PostgreSQL. Are there any other techniques or tools commonly used for high availability with PostgreSQL?
Linux HA is a popular choice, but there are other options available, depending on your specific needs and infrastructure. Some organizations use specialized load balancers or failover solutions designed for PostgreSQL, while others might leverage cloud-based services that offer high availability features.
It seems like there are many ways to achieve high availability with PostgreSQL. How do I choose the right approach for my situation?
The best approach depends on several factors, including your budget, your technical expertise, your tolerance for downtime, and the complexity of your infrastructure. You need to carefully consider your requirements and research the available options to find the best fit.
This has been a really insightful exploration of high availability and its importance for PostgreSQL replication. It's clear that keeping data safe and accessible goes far beyond just setting up replication. It requires a comprehensive strategy that includes monitoring, conflict resolution, backups, and high availability solutions.
You've summed it up perfectly. Ensuring data integrity and availability is an ongoing process, requiring careful planning, implementation, and continuous monitoring.
I'm starting to see that PostgreSQL replication is a deep and multifaceted topic. We've covered a lot of ground, but I'm sure there's still much more to learn.
You're absolutely right. There's always more to explore when it comes to PostgreSQL and its powerful replication capabilities. Before we wrap up, I'd like to leave you with one final thought to consider.
I'm ready to hear that final thought. What else should I be thinking about as I delve deeper into PostgreSQL replication?
We focused a lot on using replication for data protection and high availability, which are certainly critical aspects. But I want to challenge you to think about replication as more than just a safety net. What if we view it as a core strategy for enhancing performance and scalability, even transforming the way we design applications?
That's an interesting perspective.
Yeah.
I've been so focused on the protective aspects of replication that I haven't really considered how it could be used proactively to improve performance. Can you give me an example?
Absolutely. Imagine you have an application that performs complex analytical queries on a large data set. These queries can be very resource intensive and might slow down your application if they're running on the same server that's handling your primary database operations.
So how can replication help in this scenario?
You can use replication to create a separate read-only replica of your database, specifically for handling these analytical queries. This offloads the processing from your primary server, freeing up resources to handle transactional workloads more efficiently.
So the read-only replica is like a dedicated analytical engine, working in parallel with the primary server. That makes a lot of sense. It seems like replication can be a powerful tool for separating different types of workloads and optimizing performance.
Exactly. And this is just one example. There are many other creative ways to leverage replication to enhance performance and scalability, for instance. You could use replication to distribute read-only copies of your database to multiple geographic locations, bringing the data closer to your users and reducing latency.
That's a great point. It seems like the possibilities are endless. When you start thinking about replication as a core architectural component, rather than just a backup mechanism, this has been a truly eye-opening deep dive. I feel like I've gained a much deeper understanding of PostgreSQL replication. Not just the technical details, but also the broader implications for application design and performance optimization.
I'm glad to hear that. Remember, the journey of learning never truly ends. Keep exploring, keep experimenting, and keep pushing the boundaries of what's possible with PostgreSQL replication.
I will definitely keep exploring. Thank you so much for guiding me through this fascinating world. I feel much more confident in my ability to make informed decisions about PostgreSQL replication.
You're very welcome. It's been a pleasure sharing this knowledge with you. Remember, the key is to start with a clear understanding of your needs. Choose the right tools and techniques. And always be mindful of the trade-offs, and never hesitate to reach out to the PostgreSQL community for help and guidance.
Great advice. I'm excited to put what I've learned into practice and see how I can leverage PostgreSQL replication to create more robust, scalable, and performant systems. Thanks again for everything.
Happy replicating.